Let's talk about climate history, topic 7. We'll start off with early climate history, including snowball Earth and the early times before the present. This diagram shows you back to 542 million years ago, and we can see we had the snowball Earth before that. Well, this may be 900 million years ago, and then it got quite a bit warmer and cold and warm and cold and warm and cold and warm and quite cold, and that cold there is the Pleistocene. The Pleistocene, or our Ice Age. What's not visible on this diagram, the Ice Age, is there in the Neogene. N stands for Neogene. Our present day temperatures are right about 0 here, and that's not showing up. That's the Holocene, and it's just too short of amount of time for it to show up. It's only 11,000 years or so. And that also includes things like the Industrial Revolution. Some people would say that from the Industrial Revolution to the modern day is actually should be called the Anthropocene, but that's not officially been established yet. So we'll stick with Holocene in this class. Let's go ahead and look at early climate history. So if we go way back 4.5 billion years ago, that would be the origin of the Earth. And the first atmosphere of the Earth had a lot of hydrogen in it, but that escaped back into space. And then the very early atmosphere had lots of carbon dioxide. And that carbon dioxide was keeping Earth warm. Remember that carbon dioxide is a greenhouse gas. And so with lots and lots of carbon dioxide, the Earth's atmosphere was trapping heat, even though the sun was not all that hot back in those days. It was a dim, young sun. The gases in the atmosphere came from degassing from volcanic activity. And so the volcanoes were giving off water vapor, carbon dioxide, even ammonia, and probably methane and various other gases. Some nitrogen would be in there too. And the water would have condensed into oceans. So the water vapor coming from the volcanoes condensed into make the oceans. And that was very early in Earth's history. Now notice there's no oxygen at that time. The main source of oxygen is from photosynthesis. Photosynthesis removed carbon dioxide from the air and produced oxygen. You probably know about that. Most people already know about photosynthesis. And these are the guys that did it way back then. So cyanobacteria, of course these are modern day cyanobacteria, but here is fossil cyanobacteria. You can see that they're very similar looking, but these are more than 2 billion years old. So cyanobacteria before 2 billion years ago were producing oxygen. They started to produce oxygen and releasing it into the atmosphere, and that caused oxygen to increase. Now if you look at this diagram, you see billions of years in the past. Here's the present day at 0. They should have put a 0 there. And then 1, 2, 3 billion years ago, 4 billion years ago, and we see CO2 and methane. Those two gases were helping to keep the atmosphere warm, keep the Earth from being very cold with that dim young sun. And then eventually life evolved and cyanobacteria, or photosynthesis, evolved. And when that really started to take off, it really increased the oxygen levels. By the time it got to about 2 billion years ago, it started to rust the ocean. So the ocean had a lot of iron dissolved in it because there wasn't any oxygen around, and so no rust. But then the oxygen combined with the iron in the ocean and made something called banded iron formations. That's when the oxygen was really started to increase in the atmosphere. And then later than that, more recently, there was another jump in oxygen until we got to our present level of oxygen in the atmosphere today. Now on this time chart we have 0 is the present day, going back only 2.5 billion years. And you can see some triangles here. Those represent glacial times. You notice that glaciations were not that common. So even today we have glaciers on the planet. We have Antarctica, and we have Greenland. So we're kind of in a glaciation, you can, depending on how you define glaciation. By the way, a GA is a giga annums, that's a billion years. So each of these are a billion years. 1 billion, 2 billions, 2.5 billion years old. This chart is giving you temperature based on carbon isotopes. And later we'll talk about isotopes. So for now, don't worry about what this means, except that this is colder and this is warmer. And we see that there were colder times that were pretty similar to today, some colder times, and then some very cold times. Back then, somewhere in here would have been the snowball Earth. And then we get into the more modern day ice age here, the Pleistocene. So a lot of Earth's history was much hotter than now. Look at how hot that was. And it was also much colder, like that snowball. In the Precambrian, here's the Cambrian right about in here. And the Precambrian is before that. And during that Precambrian, there was a time when there were snowball Earth. In other words, we have evidence that glaciers existed at sea level at the equator. And that means if you have glaciers at sea level at the equator, then most of the Earth had to be covered with glaciers. It was very, very cold back then. But then since then, if we look at expanding this last little bit, in other words, 500 million years here, there's 500 million right there. There's the Cambrian, and this is the Precambrian. You can see it was really warm, and then it cooled off. It got cool, quite cold, in the Carboniferous. C stands for Carboniferous. We'll talk about that in a minute. And then it warmed up, and it was really quite a bit warmer. So all of these charts are colder and warmer. And then we get to the modern day, pretty chilly temperatures. Even today, it's chillier than most of Earth's history. Back there in the Cambrian, we had trilobites. You might have heard of them. They're relatives of the horseshoe crab. During the Carboniferous, the reason it's called the Carboniferous is because there's lots and lots of coal deposits, and coal is mostly made of carbon. So here we have forest. First forest to grow existed in the Carboniferous, and they extracted so much carbon dioxide out of the atmosphere and deposited it in the ground. There weren't things to cause that carbon concentration to decay because they hadn't evolved yet. They weren't used to eating forests. And so the carbon got preserved and got locked up in rocks and became coal deposits. Many of those coal deposits we've been mining today and releasing that carbon back into the atmosphere in the form of carbon dioxide and increasing the greenhouse effect. So you can think about that carbon getting locked away in the coal deposits back then, and that chilled the climate. So the greenhouse effect decreased, and that caused cooling of the whole planet. But later than that, it was really warm. It got lots warmer. Here we see a diagram of a map of the United States, well, North America, and you see there was a sea all the way across. This is called the Cretaceous Interior Seaway, and that went all the way across what's now the Great Plains, but also parts of the Rocky Mountains weren't there at that time, and there was a big seaway across there. Part of the reason for that seaway is that there were no glaciers on Earth. The climate was so warm that there were no glaciers, and so the oceans were higher because all the glaciers had melted and flooded in across that seaway. There's another reason for high sea levels also, because just at that time there was a lot of divergence of plates and mid-ocean ridges that were displacing seawater. So there were ocean mountains under the sea, called mid-ocean ridges, that were displacing some of the seawater and causing it to spill over the land. If you're interested in that, you can ask me about that personally. That's a geological topic. Okay, so we had all sorts of critters, including dinosaurs back then. You know about the Jurassic. The Jurassic was a time of dinosaurs. Well, so was the Cretaceous. Spelled with a C, but we write it as a K for the symbol for Cretaceous. And there were also lots of very large marine reptiles. So those are the marine reptiles. Then we get to the tertiary. Let's go back to that chart and see if we can find where the tertiary is. It's not labeled on this diagram. It's tertiary is part of the Paleogene here. So we've got the Paleogene and the Neogene, and the tertiary kind of includes part of the Neogene and all of the Paleogene. So tertiary is more recent times after the dinosaurs died out. And there was an overall cooling trend during that time with some additional interesting events. For example, so here's a chart, and you can see overall this is the temperatures of the Earth represented by oxygen isotopes this time. And again, we'll talk about isotopes later. But we see that overall there's a pattern of cooling. But we have a few interesting events. So right here is the end of the dinosaurs. That's kind of interesting. In addition to that, we have something called the PETM. That was a sudden jolt of high temperatures that occurred. And we have the Eocene optimum, and what we mean by optimum is at the warmest temperatures during the Eocene. And then it started to cool off, and glaciers started to grow right about here. We have at the beginning of the Oligocene, we have drastic cooling, and then Antarctic glaciers started to grow. Before that, there were no glaciers, not even in Antarctica. And then cool Oligocene, and then we had an Antarctic thawing, so it got warm again, and then things gradually started to cool down again with another Antarctic reglaciation. And then since then, we've had glaciers in Antarctica pretty much continuously until the modern day, including now, even though we're in a warm time, relatively warm compared to the Pleistocene, but still cold enough to have some glaciers on Earth. So overall pattern of cooling. This symbol, that's a Greek letter lowercase delta. You're probably used to an uppercase delta, which is a triangle. This is the lowercase delta. It looks a little bit like a D. Yeah, I don't know. Anyway, that's a lowercase delta. And this symbol means the change in oxygen isotopes, with 18 representing a heavy oxygen. Regular oxygen has 16, a weight of 16, and this one's extra heavy, having 18. And it's something that helps us to measure temperature of the past. So oxygen isotopes is a proxy for temperature. And when we use the word proxy, we're talking about something that can substitute. Okay, if you have a proxy, like for stocks or something like that, if you have a proxy, or if you have a proxy vote, you're having somebody substitute for you to give that vote. Well, a proxy for temperature would be something other than a thermometer that can be used to determine the temperature. So oxygen isotope is a proxy for temperature. That's this right there. That symbol, that's that symbol. Oh, by the way, per mil means per 1,000. I know it sounds like it ought to be per million, but it's not. It's per 1,000. And then here's temperature. Polar ocean equivalent change in temperature. There's that capital delta, and then there's temperature in degrees C. Okay, so comparing this to the polar ocean equivalent, in other words, they were measuring the oxygen isotopes and correlating those with polar ocean temperatures so that they could figure out the temperature from the oxygen isotopes.